Hi, welcome to AP Calculus. Tonight we're going to take a look at Chapter 7, Applications of Integration, beginning with 7.1, Area of a Region Between Two Curves. So focusing on the diagram that you see in front of you, we're going to call the blue function f of x. And we're going to call the red function g of x. We know that integrals stand for area under a curve. So therefore, if I want to find the area between the two curves, all I need to do is take the area underneath f of x and subtract the area under g of x. Now, where do we want to do this? We want to focus on, for this example, where the two curves intersect each other. So we're going to say if this first intersection point right here occurs at x equals a, and the second intersection point right here occurs at x equals b, then we're going to use the following formula to find the area between the two curves. This will just be the antiderivative from a to b of f of x, the top curve, minus g of x, the bottom curve, dx. Now that's no different than finding the area underneath f of x by doing the antiderivative from a to b of f of x dx, minus the area under g of x, which would be the antiderivative from a to b of g of x dx. So this is the application that we're going to be focusing on in all of our examples tonight. So let's take a look at our first example. It says find the area of the region bounded by the graphs of y equals x squared plus 2, y equals negative x equals 0, and x equals 1. You'll notice that in the region we have graphed here that the blue graph and the red graph do not intersect with each other. But we are given boundaries for our area that we'll be talking about. So we want to go from x equals 0 to x equals 1. Clearly that's going to be starting on this left-hand side at x equals 0 and continuing all the way over to the right side of the graph where x is equal to 1. Now let's identify these two graphs. The first function, y equals x squared plus 2, is of course a parabola that has been shifted up 2 units. So that seems to be our blue function right here. Y is equal to x squared plus 2. The other function, y equals negative x, is our linear function with a slope of negative 1 and a y-intercept of 0. So that's the red function on my graph. So if I want to find the area between these two curves, I'm going to say that the area is equal to the antiderivative. We know that we want to start on the left side with 0 and go to the right side at 1. And we're going to take the top curve, x squared plus 2, and subtract the bottom curve, negative x dx. So it's always going to be top minus bottom. You'll notice that this red curve does dip below the x-axis, and that's absolutely okay. We can take that area just by taking top curve minus bottom curve. So I'm going to simplify this first of all and say this is the antiderivative from 0 to 1 of x squared plus 2 plus x dx. This is a nice easy antiderivative to do, so this is going to be a 1/3 x cubed plus 2x plus x squared over 2 evaluated at 1 and at 0. So our area will be equal to, let's substitute the 1 in first, so we've got 1/3 plus 2 plus 1/2. And then when we substitute 0 in, we're going to get 0 plus 0 plus 0. I can find a common denominator, so that's going to be a 2/6 plus 12/6 plus 3/6. Giving me a final answer of 17/6 for the area between those two curves. Let's take a look at example number 2. Make sure you're taking time to pause the video and write these examples in your notes, as well as drawing the sketches, because obviously the sketches are really important for these areas. So for number 2, it says, find the area of the region bounded by the graphs of f of x equals 2 minus x squared and g of x equals x. And again, we're not seeing very complicated examples in this situation at all, but it's important to recognize how to find the area between the two curves. So identifying my curves, I see that f of x equals 2 minus x squared. That's definitely an upside down parabola, so that's going to be my blue curve. F of x is equal to 2 minus x squared. The red curve is, of course, going to be g of x is equal to x. Now again, it's important to set up our antiderivative so that I am taking the top curve minus the bottom curve. So we're going to say the area between the two curves will be equal to the antiderivative of the top curve, which is the blue curve, 2 minus x squared, minus the red curve, which is below, minus x dx. Now in this example, we were not given the boundaries to use as far as the left and the right endpoints where my areas begin and end. So we can probably read this from the graph, but I want to caution you against doing that because there are many instances where it looks like we've got intersection points, but it doesn't actually equal what we think it is. So we're going to algebraically calculate these intersection points. If we set the f of x equation equal to the g of x equation, then that should tell me where these two graphs intersect each other. So I'm going to go ahead and set my equations equal. So 2 minus x squared would have to be equal to x. If I move all of my terms over to the right side of the equation, leaving a 0 on the left, I'll have x squared plus x minus 2 equals 0, which is just a quadratic equation that I need to solve. This makes sense because I know that I've got 2 points of intersection between my linear function g of x and my quadratic function f of x. This one happens to be factorable, so I'm going to say x plus 2 times x minus 1. Now, if we have any situations where I cannot algebraically solve by doing something like factoring or possibly quadratic formula, then yes, we will be using our graphing calculator to find intersection points as well. So when I go ahead and set these factors equal to 0, I see that my left endpoint right over here is going to be where x is equal to negative 2, and my right endpoint is going to be x equals 1, and that's going to be this point right here. And again, I could easily have read that from my graph, but I want to make sure that I'm checking those endpoints for my boundaries. So my antiderivative is going to begin at negative 2 and go to 1. Let's go ahead and do my antiderivative. So that's going to be a 2x minus x cubed over 3 minus x squared over 2. We're going to evaluate at 1 and at negative 2. So I get, when I substitute 1 in, I'm going to have a 2 minus 1/3 minus 1/2. Now I need to substitute negative 2 in, so that's going to give me a negative 4 minus negative 8/3 minus 2. So just real quickly doing these calculations, I'm getting 2 plus 4 is 6, plus 2 is giving me 8 for the whole numbers. For the fractions, I've got a negative 1/2, then I've got a negative 1/3 minus, subtract, and a negative 8/3. So that's giving me negative 1/3 minus 8/3, which is negative 9/3, or negative 3. 5 minus 1/2 is giving me 4.5, which would tell me that the area between those two curves is equal to 9/2. Let's take a look at our last example. Find the area of the region between f of x equals 3x cubed minus x squared minus 10x and g of x is equal to negative x squared plus 2x. So again, labeling our curves, I think it's pretty apparent that the red curve is going to be g of x equals negative x squared plus 2x. And the blue curve is going to be the cubic one, so that's going to be f of x, which is of course equal to 3x cubed minus x squared minus 10x. So I'm going to set these up so that I'm finding my points of intersection. I can see one point of intersection here, one here which looks like 0, and another one over here. Again, I can kind of guess at what those intersection points are going to be, but let's practice finding them algebraically to be sure that we've got the right numbers. So set my f of x function equal to my g of x function. If I add x squared to both sides of the equation, I can see that that's going to cancel the x squared terms. If I subtract 2x from the right side and the left side, I'm going to get 3x cubed minus 12x equals 0. And again, I know that I've got 3 intersection points, and that makes sense because I've got a cubic function to solve. If I factor out my 3x, that's going to leave me with x squared minus 4 equals 0. And I then see the intersection points x equals 0 and x equals plus or minus 2. So here I have x equals negative 2. Here I have x equals 0. And over here, x equals 2. Now, when I'm trying to find the area between two curves, I actually see that I've got separate sections here. So it's the part that's enclosed. So I'm going to start with this part that's over here, and I'm going to shade that in a little bit so that we can see where we're going with that one. And I'm going to color code my antiderivative. So where that blue shaded area is, that's going to be the antiderivative starting at negative 2 and going to 0. For this one, the blue curve is on top, so 3x cubed minus x squared minus 10x. The red curve is on the bottom, so I'm going to subtract the function negative x squared plus 2x. And we'll put our dx at the end. But then I want to continue finding the area between the two curves, so this time I'm going to color this part in red because there's some more area between the two curves. That antiderivative is going to start at 0 and go to 2. This time the red curve is on top, so negative x squared plus 2x. And we're going to subtract the blue curve, so that's going to be 3x cubed minus x squared minus 10x, and of course there's a dx at the end of that one as well. Now what I'd like you to do is take a few minutes to simplify each antiderivative, take the integral of both of them, substitute your values in, and then come back and compare your answer with mine. Welcome back. Compare your work with mine. We had set up our antiderivatives together, but then when I simplified the first antiderivative from negative 2 to 0, I was able to cancel some of the like terms, so I'm taking the antiderivative of 3x cubed minus 12x. So go ahead and do that antiderivative by the power rule. So that's 3/4 x to the 4th minus 6x squared. Substitute the 0 in first, and then the negative 2. When I did that work, I ended up with a final answer of 12. That's right there. Now, for the second antiderivative, this one right here, again combining my like terms, I was able to simplify to the antiderivative from 0 to 2 of 12x minus 3x cubed. Taking the antiderivative by the power rule and then substituting 2 in first and then 0, I also got an answer of 12. So I can see that there's definitely some symmetry going on here, although it doesn't look like it when I look at my graph. When I add 12 plus 12, that's giving me a final area of 24 for the area between the two curves. Thanks very much. Take a look at the problems that I have assigned for tonight. And please practice the area between two curves before class tomorrow. Have a great night, and we'll see you next time.